Welcome to the Viva. Our project is noise assessment and localization in London Underground. In a metropolitan city, especially a city like London with large population, public transport is highly demanded. According to the records, public transport accounted more than one-third of the trips in London in 2008, and it is just 1.5% lower than the private transport. And the United Nations estimated that with the development in transportation and avoid from the traffic congestion, more people will choose to use public transport in the future. And among these transportation, the underground plays an essential role. Recently, some media reported the noise in some area of London underground is above 100 decibels, which is beyond the limits of the work regulation. This may lead to physical damage like noise-induced hearing loss to the passengers or the workers. So in this case, our goals are to design and build a sound level meter to detect the noise as well as its location. The measurements were taking place in two typical lines, which are Victoria Line and the Northern Line. And in the end, the results were shown on a cloud map. Besides, since the GPS signal cannot be transmitted to the underground, we use an accelerometer to replace it. Okay, let's start with the design of the measuring device. For the design of sound level meter, it mainly consists of two sections, the microphone and the amplifier. They are all powered by a 5-volt DC voltage. For the microphone, it is used to collect noise and convert it to electrical signal. The type we chose is AOM 6545PR. That's because it can cover humans' normal hearing range from 20 Hz to 20 kHz. And compared with other commercial microphones, it has a relatively large sensitivity at around -42 dB. And to enable the microphone operating at 4.5 volts, a resistor is connected in series, working as a potential divider. And the output is connected to the inverting input of the operational amplifier. And between these, a capacitor is used to remove the DC offsets. In addition, for the purpose to keep all the output from the microphone positive, a biased voltage of 1.65 volt is added as a non-inverting input. The amplifier is used to enlarge the change in output, makes it more obvious to detect as well as increase the accuracy. The type we chose is AD8032 because it doesn't need a negative voltage to charge it, which is more convenient for the measurements on the underground. And for the gain, we ideally want to make it as large as possible, but it cannot be beyond the range of the analog input of the microcontroller. So the final maximum output range is between 0 to 3.3 volts, and according to the largest output without amplifier measured is 90 millivolts. So the gain is finally fixed as -12.3. Then, for the localization part, the circuit is shown in the graph on the right-hand side. It is mainly based on the accelerometer, ADXL335, which has three axes, X, Y, and Z. It operates at 3.3 volts, and the reference voltage is half of this, which is at 1.65 volts. And from the datasheet, the sensitivity is 0.33 G per volt. However, for normal tube, the accelerator is always below 1.2 G. So the output is relatively small, and in order to match the inputs of the microcontroller, amplifiers are required. In addition, the amplifiers are required in each axis with same configuration. Another part is a microcontroller. The model we chose is the TNC 3.6. The reasons are that it has an ADC with 12-bit resolution and a fast 4-bit wide SDIO. And compared with other microcontrollers like Adreno, it has an onboard SD card slot and high read and write speed. And the main function of the microcontroller is to convert the analog signal from the microphone and accelerometer to discrete digital signal. This step includes sampling and quantization. After that, the digital signal is transmitted from ADC to first in, first out buffer, then to the SD card. There are two more components used in the device. The power is provided by a power bank which can produce 5-volt DC voltage, and a shield made by 3D printing is to protect and fix the circuit boards. The last step to build the device is the calibration. The calibration of the microphone was done in an open field with the help of sound pressure level meter and a frequency tone generator. The tone generator is supported by an application of the mobile phone, and it is placed in the exact middle of the SPL meter at the microphone to make sure they receive similar power. And sponge is placed opposite to the tone generator to reduce sound reflection. Furthermore, during the calibration, the sound volume of the mobile phone is fixed, only the frequency changed. The calibration was done in the frequency range of 50 Hz to 7 kHz, and the corresponding sound level is between 60 dBA and 100. Then we come to the measurements and data analysis part. The measurements were made in Victoria line and Northern line, and in order to increase the accuracy, we chose the most middle carriage, and the device was placed on the windowsill of the carriage. Besides, the height of the windowsill is similar to the height of people sitting on the chair, which has similar noise level, as people heard. After measurements, all the audio and location data were stored in the SD cards as discrete digital numbers. To analyze the raw data, the results were separated to audio and location information separately, and we use MATLAB to translate and parsing. After translating from the MATLAB, the data were mapped on a graph, which is equivalent to continuous sound level versus time, and there is an example shown in the figure, which is the southbound of Victoria line. However, during the analysis, an unknown signal always shows up at around 6 kHz, and through the testing, this is from the circuit itself instead of the noise in the carriage. To remove this, we could use a software-based band-stop filter. Then for the localization part, we used the equations in the slide to calculate the displacement, and by comparing to the distance between stations provided by TFL, we can get the location information. Finally, we come to the results. These are the color maps of Victoria line and Northern line in southbound and northbound respectively. From the images, we can get the noise level for most areas of these two lines are above 100 dBA, and in some areas even beyond 115 dBA, especially in the Northern line. And these are very harmful to people's health. And at the end of this project, we hope the results are useful for the people who always taking the underground in those noisy areas. And that's all my presentation. Thanks for watching.